Hello judges, we are InfoHawk and we're presenting a solution that transforms the MOD's project delivery bottleneck into a proactive, data-driven solution. This is our team. The MOD have faced significant challenges in project delivery due to poor data management systems. This leads to delays, inconsistent outcomes, and reduced focus on high-value activities like analysis and strategic insight. Currently, the MOD uses the PEAT tool to manually guide project setup and evidence requirements. Teams spend excessive time creating documents that don't answer the necessary questions. Our key persona is a project delivery lead. Due to improper data management, they currently struggle to find the relevant documents. They also must manually review documents upwards of 60 pages to ensure that the project aligns with the MOD's demands. The opportunity lies in using large language models, or LLMs, to identify evidence sources across project data and visualize it on a dashboard that displays evidence, maturity status, gaps, and connections across all project areas in real time. Success means creating a solution that reliably identifies relevant documents and evidence and provides explainable recommendations.
We employed an assistant within IBM Consulting Advantage to conduct an as-is analysis which revealed the key problem area, John's manual data extraction across multiple sources. These insights directly informed our solution architecture, ensuring we address real user needs rather than perceived problems. We utilized Miro to create a structured solution. This included identifying pain points, defining the problem, and aligning on our product vision, persona, and value proposition. We used story mapping to plan the user journey and anticipate future challenges. A Kanban board helped us manage tasks efficiently and keep the team aligned. This visual workflow demonstrates our systematic journey from initial problem discovery to final solution architecture, ensuring every decision was grounded in user research and validated through iterative testing.
The process begins with either a project number or a set of project documents, and these serve as an entry point for our system. If the project number is supplied, the system performs a RAG, Retrieval-Augmented Generation search, to grab the relevant documents as well as checking file names for matching project numbers. If documents are provided, a machine learning model will compare them to historically submitted documents. This helps identify if expected files are missing, highlighting it as a warning or recommendation. Users can submit questions, and these are fed to the system to help build the query that guides the next steps. The system constructs a query based on both the documents and the user input. The query is sent to the locally deployed LLM model, which returns a structured JSON output. Next, a red, amber, green maturity score is given. The user can then go back to the LLM to help it suggest how to improve using a query-based editing. Finally, the results are displayed, giving clear insights based on their questions and project documentation. Here is our AI tool. It has the documents that it needs, and we're going to ask it this question. Essentially asking it, have all relevant stakeholders been identified? We got this from the PEAT tool, Excel file. Here are our results. It's in standard JSON format, so it can be read by our front end. And as you'll see, it will rate the context documents on a red, amber, green maturity scale with evidence. I can use query-based editing to ask for suggestions. I'm going to ask how this can be made to green. This response will tell us what edits to make to ensure the document aligns with need and prevent unnecessary delays to projects.
Here's the landing page for the AI PEAT tool. You can see it's nice and simple for the user. The front screen shows us all the projects down the left-hand side, and you'll see the top tab refers to some of the questions we asked the LLM model. The table shows us a red, amber, green status for each project question, which shows how mature the documentation is in achieving the criteria. It also adds to the functionality of what the team need to work on. So, for example, all projects are really bad at sustainability, so you might choose to run a sustainability workshop to improve this. All the project delivery team need to do is to select a project to see further details in the summary page. In the top right-hand corner of the summary page, the project box shows the project selected on the previous page to ensure you're looking at the right project data. The table in the top left shows the project index and the questions we asked the LLM. When you click on the relevant project index and the question, it gives you the red, amber, green status of the confidence level along with the description of the logic behind it. Then in the table in the bottom, it shows the response with the evidence details.
Our next steps to improve the solution include fully integrating the architecture solution with the process listed below.
For our proof of concept demo, we chose to use OpenAI's O3 reasoning model, as it's quick to get up and running, required minimal infrastructure, and provided strong out-of-the-box performance. For full production for MOD, we'd only consider offline models produced by aligned countries that allow in their policy for us to use them for military use. In the current landscape, this would have us looking at models like Mistral, MTP, or Stable LM, but we'd need to do some model comparison for this use case to decide which specific models to use, potentially with some fine-tuning needed. The disadvantages for using offline models are mainly around the resources, GPU power, and suitably trained personnel required to run and maintain these models. However, using offline models erase most of the concerns around data privacy and allow for direct ownership and control of technology. We aim to build our tool using Python, leveraging the LangChain framework due to its maturity, modularity, and strong community support. LangChain provides robust integrations for training LLM calls, managing memories, and orchestrating retrieval workflows, making it ideal for our RAG-based system. For vector storage, we plan to use Pinecone, which is a scalable and production-ready vector database that offers fast semantic search capabilities and seamless integration with LangChain. To generate the embeddings, we aim to use a nomic embedding model, which offers high-quality, open-source embedding optimized for semantic understanding and retrieval tasks. We would build the tool in VS Code IDE due to its rich ecosystem, excellent Python support, and seamless integration with tools like Git, Docker, as well as built-in debugging. By design, the system can handle and support multiple concurrent projects due to our retrieval step being able to retrieve based on the document's semantic content. This means whether documents are not explicitly labeled or shared around projects, the system can intelligently surface most contextually relevant information by understanding the meaning behind the text, ensuring accurate project-specific responses. Also, because we won't be siloing the content by project, it can draw on evidence used for other projects or work.
Oh, and in case I don't see you, good afternoon, good evening, and good night.